Good morning, students. Today we are going to see about Newton's law of universal gravitation, or simply Newton's law of gravitational. And this Newton's law of gravitational deals with force of gravity. As you know, force of gravity is one of force in nature from four dominant force. For example, we do have gravitational force, which is a weakest force, nuclear force, electrical force, and the strong nuclear force, weakened strong nuclear force. And one of these four forces, gravitational force, is a force that exists between two bodies, and it states that every mass in the universe attracts every other mass with a force that is directly proportional to the product of the two mass and inversely proportional to the square of the separation distance between them. And mathematically, this can be expressed as gravitational constant times the mass of body 1 times the mass of body 2 over a separation distance square. The separation distance is a distance or a gap between the centers of the two bodies. Therefore, this force has some natures. The first one is, since it has a small constant value, then the force is said to be a weak force. And the other one, it is directly proportional to the magnitude, the product of the magnitude of the two mass, and inversely proportional to the separation distance between the two bodies. Therefore, it is governed by the inverse square law. When you say inverse square law, the magnitude of the force is not depend on the separation distance, but it is depends on the square of the separation distance. So it holds the square, the inverse square law. Then we can just say 2 points here. The first one is force is directly proportional to the product of mass 1 and mass 2. And the second point is force is inversely proportional to the square of the separation distance. So these 2 points are very important points. And the other one is this force must exist between two bodies. So the force exists between two bodies, and this force is a weak force, the weakest force in nature. And the other one is this force has an effect when the mass of the two bodies is large. It needs to be large. The mass needs to be large. Force m2 over r square. This force is comparable with gravitational constant, simply gravitational constant or universal gravitational constant. M1 and M2 is the mass of the body, and R is the two bodies. For example, dealing with a force that exists between sun, from the center of the sun up to the center of the earth. Or even for taking two particles as an example, then the distance will be from the center of particle 2. Then this separation distance is considered as R, and there is an attraction force. And the other very unique nature of this force is it is an attractive force. It's not repulsive force, but it's always an attractive force. For example, for electrical force, it can be attractive or a repulsive force. Whereas for gravitational force, it's always an attractive force. No repulsion between two mass, but there is an attraction, or there is always an attraction between the two masses. Okay, the other point that we need to know here is there is an acceleration due to gravity. This acceleration results due to the net force, which is gravitational force. Then from our previous knowledge, the net force on a given system is mass times acceleration. For example, if you are talking about the weight of an object, it will be mass times gravitational acceleration. And we have said that gravitational force is expressed by g times mass of a body, maybe near to the surface of the Earth, times mass of over r square. Then from this, if it is equals mass times g, then if we cancel mass, small mass by small mass, then we left with g equal capital M over r square. Assume we are considering a body near to the surface of the Earth. Then the two bodies are the mass of the Earth and the body which is placed near to the surface of the Earth. Then the gravitational acceleration due to this body on this body due to the mass of the Earth is g times mass of the Earth over, since it is near to the surface of the Earth, then the separation distance will be the radius of the Earth. Then we can calculate g by substituting the value of gravitational constant. The mass of the quantities are constant. We know that g is 6.67 times 10 raised to minus 11, and we know the mass of the Earth, approximate value of mass of the Earth, and the radius of the Earth. Then by substituting these values, we can get the value 9.81 meter per second square. This value is acceleration due to gravity near to the surface of the Earth. This should be near to the surface or on the surface. So on the surface of the Earth, the gravitational acceleration is 9.81, which is a constant value. But this value may not remain in any parts of the Earth. For example, there may be variation at equator and at a polar region, but on average it is 9.81 meter per second square. And the other one, this value varies based on the place where the object is placed or found. For example, if this is Earth, and the other one, if you put an object which is at a height of h from above the Earth, let's be this one is a body with mass m, and the mass of the Earth is capital M. Let's say the mass of the Earth is capital M, and there is a distance r, which is the radius of the Earth, and a height h, which is a height that an object is placed. Therefore, the total distance or the total separation distance from the center of the Earth up to the place where the object is placed will be r equals small r plus h. Then our separation distance is radius of the Earth plus a certain height h. Then the gravitational acceleration now will be g equals gravitational constant times mass of the Earth divided by radius of the Earth plus h the whole square, because the separation is radius of the Earth plus a height h, because the object is placed above at a height of h above the surface of the Earth. Then what do you expect the value? What will happen on the value of a gravitational acceleration? Will it increase or decrease? As the height of an object is increased, then the value of gravitational acceleration will decrease. At a certain height h above the surface of the Earth, then gravitational acceleration will get less. Therefore, the altitude or the height above the surface has an inverse relation with a gravitational acceleration. When we're going to the center of the Earth, then gravitational will increase due to the less separation between the object and the center of the Earth. So we can calculate acceleration due to gravity at any height by adding the height on the radius of the Earth. Okay, the other point that we need to discuss today is Kepler's law. This Kepler's law of planetary motion describes the motion of a planet around the sun. As you know, in our solar system, sun is taken as a fixed point, and then a number of planets will revolve around the sun. Then this Kepler's, which is the name of a person, and has described this situation. And there are 3 laws, and we do have Kepler's second law and third law. And the first Kepler's law says the planets orbit the sun in the elliptical path with the sun at one focus. So the shape of the path is another. The orbit, the shape of the orbit is elliptical, not circular, but it is an elliptical shape. The path has an elliptical shape, not circular, and the focus is the sun. For example, if we have sun and the Earth, for example, one of the planets is Earth, whose shape is an elliptical. This one is Earth. This is sun. Then sun is taken as a, and Earth is revolve around the sun. Therefore, this situation that planets revolve around the sun is described by Kepler's first law. So Kepler's first law describes the path of a planet that revolve around the sun, and this law takes sun as a focal point, and the path is not circular but is an elliptical. And the second law relates with the area. For example, when planets revolve, sometimes they will revolve being close to the sun, and sometimes sun being far apart from the sun. There are an extreme points. Sometimes they will be near to the sun, and at the other point, they will be far from the sun. Whereas when they are moving, being far from the sun, they will have some distance to cover, and that distance or that area will be related with time, and the time taken to cover equal area will be an equal time interval. For example, if they take to cover a certain area 1 month for Earth, for example, and in 1 month the sun, the Earth will cover an equal area despite its closeness and farness. Therefore, the area will be related with the time interval. And Kepler's third law states that the square of a period of a revolution of the planets are proportional to the cubes of their mean distance from the sun. For example, we do have sun, and any planet is revolving around the sun, and the distance from the sun up to the planet is not equal. For example, this may be if it is R1 and S1 is R2, R1 may not be equal to with R2. For example, for this case, R1 may be greater than R2. And we have to take an average distance rather than taking one of the distance. We have to take a mean distance on or an average distance, and this average distance assume is R. Then the square of the period one complete revolution. For example, for the Earth, period is 1 year. For other planets, the period will vary. Divided by a mean distance, then we get a constant value, and this constant when a period is the period square is variation distance, a constant value, and this constant value is 4 pi square divided by g times mass of the planet. G times mass of the planet. G is constant, and the 4 pi square is constant number, and the mass of the planet is based on a mass based on the given planet. For example, Earth and Jupiter do not have equal mass, so it depends on the given planet, but the ratio t square over r square r cube remains constant. And the other one, even we can take, for example, period square over mean distance 1 square cube equals period 2 square divided by mean distance 2 cube. So we can calculate if we know one of the planet period is known and the mean distance is known, even we can relate one of the planet's period with other one. So this the types of motion that a planet move around the sun is described by Kepler's law. There is maybe a detailed explanation, but this one is as an introduction part. So Kepler's has 2 laws. The first law states that the planet orbits the sun in elliptical paths. A body that rotates on the sun is said to be planets. Not only planets, there are some celestial bodies, but the planets will rotate around the sun by taking sun as a focus, and the paths that follow the planets are called elliptical paths. And the second one is the line joining the sun with the planet sweeps out equal areas in equal interval of time, just to cover if despite the farness or the closeness, if they are close to the sun, they have to be fast, or if the planets are revolving, being far from the sun, they will move with a slow speed, despite their fastness or slow, they will cover equal area in equal interval of time. Then to sum up, Newton describes universal laws. There are a number of laws. One of the law is gravitational law, and this gravitational law relates particularly the force that exists between the two masses. Force is always attractive force, and due to their universal gravitational constant, the force has small magnitude or a weak force proportional to the product of two masses and inversely proportional to a separation distance square and the difference. For example, gravitational force and electrical force. Gravitational force is Newton force, and electrical force is a Kepler's force.
ሚስተር እንውጣ